Hey, everybody. Can you hear me okay in the back? Can everybody hear me? Awesome. Welcome to today's talk. We're going to be talking about LLMs, AI, MCP, and the title of the talk is Agent 007, Licensed to MCP. I don't know. Anybody seen that film? Yeah, so it's going to be, let's keep it pretty interactive. If at any point you have a question, feel free to raise your hand. I will also have time in between for Q&A. So quick about me, I've been doing natural language processing for a long time. Before LLMs were a thing, I don't know if you guys remember like word to vec and RNNs and all these types of things. I've been doing NLP for a long time. I studied math and computer science in university. I've got a bit of industry experience at a bunch of big tech companies. And I'm very interested in leveraging AI to improve developer productivity. So that's quick about me. About the talk, we're going to kind of split it into three sections. We're going to be doing an overview of what agentic AI is. We're going to dive deep into Model Context Protocol, or MCP. You might have heard of this. And if we have time at the end, we'll do a bit of a live demo. And just to kind of gauge everybody, who here has heard of LLMs? Who here knows what an LLM is? Okay, that's pretty much everybody. Who has heard of MCP? Okay, yeah. And who has heard of agents or agentic AI? Cool. Okay. So yeah, let's dive right into it. So agentic AI. So when we talk about agents, this is like a really overloaded term these days. But when we talk about agents in a artificial intelligence sense, in the most general kind of way, an agent is something that can perceive an environment and use planning or knowledge or some basic set of rules to take an action which can change the environment. And when you talk about artificial intelligence can be defined even as the study of agents. But this is a really broad definition. Like by this definition, a thermostat is an agent because it perceives the temperature and follows some rules to change the temperature of the room. It takes an action to change the temperature of the room. And by this very definition, humans are also agents. Um, so we're going to go from this definition to like LLM agents. Um, so here's an example of a very simple agent. This is called a reflex agent. You have some environment, it can perceive the environment, and it uses some rules to decide what action to take. And the action might change the environment, and you get into this kind of loop. But you can also have more complex agents like this, where it's storing some state from previous percepts of the environment. It's trying to predict what its action would do to the environment before it does it. It's trying to maximize some utility function or try to meet some goal. And these are all agents in the kind of theoretical sense, in the artificial intelligence sense. And I'm going to give you a brief history of agents in AI. And it goes all the way back to the 1960s, where computers were like as big as a room. And this is a computer program called ELIZA. And it's a chatbot in the 1960s. And you can see Eliza's talking to somebody, something troubling you. The men are all like, what is the connection, do you suppose? And Eliza like doesn't actually understand language. It's just very simple heuristics, pattern matching keywords, but it gives the illusion of intelligence. And it, I guess you could say its goal is to just maximize the length of the conversation. But we also have physical agents. In the 70s, this is Shaky the robot. He has all these sensors, and he can traverse a room and fulfill some objectives, like take the red ball across the room. He's called Shaky because he shakes a lot. And so he gets input from the world through these sensors, and he has a computer program inside him with fairly rigid rules about what actions to take depending on the inputs. Step forward a couple of decades, we reached Deep Blue, where we have essentially an agent who beats Garry Kasparov in the game of chess. And this was a pretty pivotal moment for AI. But when you talk about agents, you can think, oh, well, this is just it's a really simple game. This is not the real world. Like, it's a very constrained game. It's turn-based. It's not real time. So even though it's a huge advancement, it's still so far away from what we want to see in like a general artificial intelligence or something like that, right? Well, pretty soon after this, we get AlphaZero. This is another step up. Even though it seems very similar, there's 30 years in between these two things. And this is a significant advancement because it represents a completely different approach to building artificial intelligence. With Deep Blue, they got a bunch of chess experts to come and create utility functions and tell the software, if the position is good or not, and stuff like that. With AlphaZero, we didn't encode any of that knowledge. With AlphaZero, for the first time ever, we were able to build agents that can learn without prior human input. And Go is also a much more complex game than chess. It has a much bigger state space. At any given position in Go, there's many more moves that you can make. From there, but you can still say, oh, it's a game, it's turn-based, and it's a very constrained kind of environment. So how useful are these agents really? A couple of years later, we see AlphaStar. And AlphaStar was a pretty big deal. And we're still in the realm of video games, but it's actually quite a big deal. And this is, if you don't know, this game is called StarCraft. And it's a very intense, real-time strategy game. And they built an agent that can play this game, which is considered like a very difficult esport kind of game. And so now you have an agent that is playing a real-time game with many different moving pieces, and a very long horizon. Like a StarCraft game lasts like 20 minutes. And so this thing is, it's learning to achieve a goal of winning over a long period of time in a much more sophisticated environment, right? And a few years later after this, we get LLMs. And I think LLMs are what is taking agents to another level. Up to this point, agents are always operating in constrained environments, in video games or board games and stuff like that. But real utility, you can think, I want to be able to talk to an agent. I want to be able to interact with an agent in the real world. And LLMs really accelerated the path towards that for a few reasons. So first of all, LLMs are quote unquote easy to train. I mean, they require a lot of GPUs, but they're easy in the sense that you have tons of training data. You can just toss all your textual data in there, and you don't need to craft any fancy reward function. It learns from the data that you give it. We also see scaling laws happening with LLMs. The more compute and the more data and the more parameters you add, the better performance that you get. And the really cool part is there's a natural language interface. For the first time ever in the mid-2010s, we can now talk to a computer using natural language. And we can get responses in natural language. And what we see with LLMs is they have emergent skills. You can train one model, it can do many tasks. It can do tasks that we didn't even think they could do, but we discover this later. And so LLMs open the door for LLM agents. And an LLM agent is something that can that overcomes the limitations of regular LLMs, combines planning, memory, and tools to service user requests. And that's a mouthful. We'll get into that. But yeah, basically, with an LLM agent, for the first time ever, we're starting to have these AI systems that can take actions in the digital environment. For the first time ever, we have AI systems that can, to some degree, actually understand natural language. And we're going to dive deep into how we got here, how these things are built, and where we go from here. So let's do a bit of history of LLM agents. It all started in 2017 with this paper called "Attention's All You Need." And this was a pretty big deal. This is where the transformer architecture, if you've heard of it, was introduced. And up to this point, everything to do with natural language processing was done with these things called RNNs or LSTMs. There are these types of neural networks that are recurrent. But with transformers, for the first time ever, they removed the recurrence from training. And this was a big deal because it allows us to parallelize the training to a much larger degree than ever before. So around 2017, we suddenly gained the capability to train way larger models way faster than ever before. A few years later, OpenAI releases GPT-3. So they start doing that. They start pushing tons of data and parameters into these transformers. And what they realize is that these models can do in-context learning. In fact, the paper for GPT-3 was called "Language Models Are Few-Shot Learners." And this is a very important graph. I want to pause on this graph a little bit. So on the x-axis here, we have the number of examples provided to an LLM in the context. So what this means is I want the LLM, let's say, to translate from English to French, or I want the model to do some task, right? At 0 on the x-axis, it means I haven't given it any example of that task. So I'm just giving it like, hey, translate the sentence from English to French. And here I've given it 10 examples of the task I want it to do. So like, hey, do this, and here's 10 examples of how to do that. And what we see on this graph is that the more examples we provide in the context, the better the performance gets. And furthermore, we see that larger models are able to make better use of more examples. And we call this few-shot learning or in-context learning. Basically, LLMs aren't just parrots. They seem to be able to do tasks that they've never seen before. And so, at this point, we start thinking of LLMs as like, hey, these things are potentially a pretty big deal. But at this point, they're still pretty rough. ChatGPT is not out yet. And when you talk to an LLM, it's like completely unhinged. And so in 2021, enter RLHF, or reinforcement learning with human feedback. And basically what we're able to do here is, this is the magic sauce that made ChatGPT what it is. And basically here, we realized that we can take a base LLM and fine tune it, do some post-training to make it better at following a user's intent. So now LLMs are much better at answering queries. They're much better at answering questions. They're much better at following instructions. And so very slowly, we're making LLMs more useful, and we're getting closer to that state of being able to use them as the reasoning core of an agentic system.
Question.
Yeah.
Can you briefly explain how is this related to hardware, like NVIDIA's chips, for example?
Yeah, sure.
All of a sudden, NVIDIA's
sure.
took off at the same time as all this.
Yeah, absolutely, sure thing.
What's the relationship?
Yeah, I'll let you know. So, before attention is all you need, before the transformer architecture, anything to do with language was recurrent, and as a result, it was sequential. So you had to train in a very sequential manner, and it didn't parallelize very well. So with the transformer architecture and LLMs, you're able to parallelize the training. So if you have more hardware, you can train faster, or you can train a bigger model. And with the scaling laws, we see that the more parameters your model has, the better performance that you get. So it's able to learn better from the same amount of information if it's bigger. And so what we see is a push to increase the number of parameters for models. We see a push to increase the data set size for these models. And the data was available. The parameters, you can set them as big as you want. So the final part of that equation is we need the hardware to be able to train these things. And GPUs lend themselves very well to training these types of models because a GPU is essentially a very parallel CPU. It has thousands of cores. It can do many operations in parallel. And so around this time, we have a greater need to train big models. We have more data. And so NVIDIA blows up because we need more GPUs to be able to do that. Yeah. Yeah.
It's the parallelism you're saying.
Absolutely, yeah. That's a huge part of it. Yeah. Okay, and then now so we have RLHF. We're able to take these like really unhinged LLMs and make them have a conversation. But the conversation is not really what we want from an agentic system. We want some sort of reasoning. We want some sort of the ability to take actions and all this stuff. About a year later, we're messing with these LLMs, and we discover something called chain of thought. And basically, before you'd ask an LLM a question, you get some output, And it's a really weird result, but what we realized is that if we ask an LLM a question and we ask it to think out loud or reason about how it's reaching its answer, and it outputs its thinking process and then outputs the answer, we get way better results on the same types of benchmarks or on the same types of questions. So around this time, we're like, whoa, these things maybe can do a bit of reasoning. These things, are more than just parrots or more than just question answering, but maybe maybe we can do more with them. Later that year, we get React, and not React like the JavaScript framework, but React like reasoning and acting. And what these guys do is they hook up a language model to tools. They create a framework for combining this reasoning ability with the ability to take actions. So for example, they combined LLMs with calculators. So LLMs are really bad at doing math by themselves. So these guys told an LLM, hey, if you ever need to do math, don't just output the answer directly. Output a call to this calculator. The calculator will give you the answer, and then you can return that to the user. It seems really simple, but it was a pretty big deal when this came out. And so for the first time now, language models are taking actions. And they're combining that with reasoning to figure out the result of their actions. And in 2023, we get AutoGPT. Did anybody ever see this? So this was like a really viral demo that came out a couple of years ago. And so this guy, I think he's like a game developer. He built this thing called AutoGPT. He hooks up, I think it was GPT 3.5 at the time. He hooks it up to a web browser. He uses the React framework to say like, hey, if you need to run some code, call this tool. If you need something from a web browser, the harness that you're in will get it for you. And for the first time ever, we have an actual usable agentic system. It's not very good, but it's a great sign of things to come. So AutoGPT goes crazy viral. People start talking about agents around this time. And a year later, we have this like framework explosion. Agents are everywhere. Everybody wants to build them. Everybody wants to use them. You have LangChain and AutoGPT and Crew AI, and we start to see a lot of standardization of the major components for agents. Like when we were talking about memory and planning, and we're going to get into that a little bit more. We start to see kind of standard implementations for this kind of stuff. And a year later, basically at the end of last year and the beginning of this year, we get Model Context Protocol, which is going to be the second part of our talk. And so now we have all of these different LLMs. We have all of these different tools that they can use, all of these different services that they can use. But everybody's like writing their own way to do things. Everybody's interpreting the React framework, or everybody's writing their own APIs and their own connectors. And so MCP comes on the scene, and it aims to standardize things a bit. And we'll get into exactly what MCP does, but let's go a little bit into like why LLM agents are even such a big deal right now. So I'm talking here to GPT-4o, very smart model, right? Super smart model. And I ask it, what is the weather in Vancouver? And it says, I don't know, right? And that's what you would expect, because a base LLM like this doesn't have access to real world information. It only has access to whatever it was trained on. And it's kind of like a snapshot, right? So an LLM by itself, it's very useful. It has a lot of base knowledge. It knows the capital of France is Paris. It knows, it has a very vast amount of knowledge, but it doesn't have access to real-time information. So that's a very big limitation of LLMs. When we want to create an agentic system, we can't just rely on LLM by itself. But they have other limitations too. They hallucinate. So even if you have a task that doesn't require real-time knowledge, you might still require accurate knowledge. So for example, let's say you want to create an AI system to summarize a law for you, or answer law questions. if you just rely on the base model, even though it has been trained on the entire book of law, it can still make mistakes because it doesn't have perfect recall. And so hallucinations are a big problem. Multi-step computations or long chains of reasoning, real-time data access. And you might have heard of RAG, or retrieval augmented generation, that solves some of these problems. But really what we want is to provide LLMs with access to data. We want to provide LLMs with access to tools so that they can look things up, so that they can take actions, and it makes them immensely more useful. And you kind of have this three-step progression. You have just your base LLMs, you give it a prompt, you get an answer. You have RAG, or retrieval augmented generation, where you're providing it context. So in the law example, I would be providing it with the relevant clause in the book of law, let's say. And that's going to give you much better answers. And then finally, you have agents, where instead of your application having to figure out what context to provide, the LLM can do some reasoning and access various data sets or databases to figure out what the relevant context for the question is. And it does that, and you can kind of think of it as having three major components: planning, memory, and tools. And for memory, you can kind of break it into short-term memory and long-term memory. So when we talk about short-term memory, we're talking about basically whatever fits into the context window of an LLM. So if you guys are aware, LLMs have a context window. There's only so much text that they can pay attention to at one time. And so in the ChatGPT sense, you can think of short-term memory as your conversation history. So it's like kind of just the buffer, right? Whereas long-term memory can go beyond that. And so you can think of an agent, for example, having a database where it can store and later retrieve facts. To go back to the law example, I'm talking to an agent about some law case that I'm working on. And way later in the conversation, we've had such a long conversation, it doesn't remember anymore what we were talking about because it's exceeded the context window. So if we're using long-term memory, it can store some of the facts, or it can even store the full conversation history of what we're talking about. And I can then ask the agent, hey, remember yesterday when we were talking about XYZ? It can go out to this long-term memory and access it and retrieve that. And so for short-term memory, there's a lot of techniques that people use. The most simple one is just a buffer memory, where you keep the entire conversation history there, or the entire task history there. But you can also think of like summary memory. So for example, in ChatGPT, if you guys have noticed this, the more you have the conversation, the more it forgets in the beginning of what you were talking about in the beginning. One thing that they do is they summarize the beginning of your conversation to condense it down and make it fit into the context, and stuff like that. For planning, there's a bunch of different planning frameworks, but really you get into a loop of reflection or self-reflection. And there's a few different frameworks. I showed briefly React earlier. This is one called reflection. And in reflection, the agent is gonna have some task. It's going to break it into subtasks, and it's going to reflect on its previous actions and its future actions. And this can be combined with some long-term memory to figure out the best way forward. So with reflection, you have this kind of analysis of the current progress and some sort of planning. But in general, when we talk about planning, when you want to build an LLM agent, you want to be able to produce a plan towards the goal and evaluate progress towards that goal. And so all of these frameworks for planning are essentially about that. And finally, we have tools. So the kind of third major components for building LLM agents is tools, where if I have a model and I want to ask it, what's the weather in Hawaii? Or what's 1,000,000 times 200,001? Instead of it using its weights, instead of it using its training data, which is going to be very prone to hallucinations and suffer from all these limitations that we discussed, instead it's going to output a call to a tool, some sort of external tool, and use the result of that call to achieve its objective. Yeah. Now, when you build LLM agent systems that are doing this kind of reasoning, doing this planning, leveraging various types of memory and tools to accomplish a task, there's a lot of limitations involved. The first one is limited context windows. There's only so much attention, there's only so much text that transformers can pay attention to at the same time. The other big problem is multitasking. A lot of the current frameworks can only do one task at a time. So to go back to ChatGPT again, it's going to search the web and then write a Python program and then search the web. And it does things very serially. It takes a lot of time. It has a lot of limitations in that way. The other big limitation is computational cost. So, when we were just doing the prompt an LLM, get a response approach, it's kind of cheap in the sense that you start to immediately get an answer. But when you take an agentic approach where before you get an answer, it's calling an API, it's doing some like chain of thought reasoning, it's writing a Python program, running it and seeing what the output is. It's doing all of this stuff under the hood before it gives you the answer. You run into a lot of computational cost. And so, you're calling the LLM more, you're calling external services more, you're doing all of this stuff. And it's just prohibitively expensive sometimes. And it takes longer. When you're querying an LLM, let's say you want to know what the capital of France is. If you just query an LLM directly, it's going to tell you Paris immediately. You're going to get the response back in less than a second. But when you query an agentic AI, it's going to be like, okay, I need to figure out what the capital of France is. Maybe I can Google it. And so it can end up taking a lot more time to do the same task. And so it's very important to know that, sometimes it's okay to query an LLM directly. Sometimes it's okay to just query an LLM with some context. And only, if that's not enough, you kind of reach for the agentic approach. And finally, I want to discuss the problem of reliability. And I have this kind of like little equation here to illustrate what I mean. So 0.95 to the power 20 is 0.35. So what does this mean and how is this relevant? Let's say I have a tool or a step in my reasoning that's 95% effective. 95% of the time it works. And you might think, wow, that's a pretty fairly reliable tool. It's a fairly reliable step in my thought process. But when you're chaining these things together, like an agent is going to do, it's going to, when you have this plan with many subtasks, and you have, let's say, 20 steps in your reasoning, now the probability that the whole chain is successful, even though it's composed of individually very effective tools and processes, is going to be very low. And so what we see with agentic approaches is right now they're very effective, really mostly for tasks that take 3 to 4 turns. So 3 to 4 Google searches, API calls, whatever. And reliability over a long horizon is a big problem. Okay, so we moved through that fairly quickly. I hope it wasn't too quick. And I'm just going to pause here, give us some time for questions.
It's always just summarizing for this loosely enough. So do you know any good approaches that can be used for this kind of issues?
Yeah, absolutely. So the question is, how do we tackle memory when the context of the task is very, very long? So when we have a task that requires so much context, or you have a chat that's so long that you can't fit into the context window of the model. So summarization is one way. But the problem with summarization is it's lossy, right? So, ideally we want it to be able to remember exact details. So another kind of memory that's very popular is the entity memory. And so entity memory, you are going to go through the context of the task, and you're going to extract any relevant entities that there are, and you're going to store them in an external database. And so let me see if I can kind of give an example of that. Let's say let's go to the example of ChatGPT. So you want to build a kind of a more agentic ChatGPT. Anytime you mention a person, like, my sister blank, you might have an entity memory system that is going to take that and store it in an entity database. So now my sister, let's say her name is Sarah, is going to be a record in this database. And later, when you're talking about Sarah, instead of relying on short-term memory to know who Sarah is, the agent can retrieve the record for Sarah from the database. So when I say, hey, what's Sarah's schedule look like, it might go reach out to that external storage. Now, to actually retrieve entities from a chat or something, you can also use an LLM. So you can have an LLM whose task is to monitor the short-term memory and extract any entities that it finds. Another way, which is a bit more automatic, is like vector memory. So there's a technique in which you can take text and create embeddings out of it. Are you aware of like creating embeddings out of text? So yeah, you create embeddings out of the context, and you store that in a giant vector database, and then you use like semantic similarity on queries to figure that out. So that's another kind of another way to do it. Yeah. Yeah. But yeah, like generally with memory, a lot of the long-term stuff, you're gonna utilize an external database, and you're gonna figure out a way to extract information from the context into that database. Yeah. Okay, so we've got a few hands up, guys. My laptop is dying. I'm just gonna plug it in real quick. Sorry about that. Okay, I didn't see who. Oh, I've got it. I didn't see who was first. I'll just start from the front and work my way back. Yeah.
Okay, so ChatGPT recently introduced memory feature.
Yeah.
What do you think? What architecture do you use? Is that vector database?
Yeah. So I think they're using like definitely like hybrid memory. So in ChatGPT, it's known that they summarize the earlier parts of the conversation history as it starts to overflow from the context window. So they're summarizing the beginning of your conversation. The memory feature you're talking about, it's a mixture of entity extraction and vector database. And you can actually see it at work. You can actually go into your settings and see the entities that it's extracted or the facts that it's extracted. And I don't think they publish details, but my suspicion is they build a knowledge graph. And a knowledge graph is when you have entities like people or facts and stuff like that. And the edges between the nodes are the relationships between these things. So for example, I can have a node which is Sarah, and then the relationship between the user and Sarah is an edge connecting those things, and it can be like a sister of relationship or something like that. And so behind the scenes, they're kind of building a knowledge graph about the user, would be my suspicion, but yeah. Okay, hand, yeah.
Can you talk a little bit more about how a model interacts with long-term memory? Like, does something need to index your document store, or like how does that work?
Yeah. So that's a great point. So in terms of actually indexing, this is kind of how that works. I'm just going to mute my phone here. Sorry. Yeah, this is kind of how that works. You have a bunch of raw data. You're going to apply some information extraction process, maybe chunk it. You're going to embed it and store it into a vector database. And your LLM, your agentic system now, when it comes time to answer a user query and it needs to use this knowledge, it's going to reach out to a tool. And so it's going to reach out and so it's going to do this internal reasoning, right? It's going to do this kind of reasoning loop of, these are the tools that are available to me. This is what the user is asking me. I think that if I take this action, I'm going to get this observation. And so one of the actions that it can take is, I have access to this database. Let me write a SQL query, execute it against the database, and see what I get. And so that's how it might reach out and get access to this information that has been indexed. Now, you can influence its behavior. So you can say in your system prompt to the LLM, if you ever get a question about XYZ, don't try to answer it directly, use this tool, or use this API to get the information you need, or something like that. Yeah. What are my thoughts on open source LLMs for agents? I think open source LLMs are great. I hope we keep making good progress there. I think that for agents in general, you want to use the strongest base LLM that there is. So the agentic process, this kind of reasoning loop, does not work with poor LLMs, with smaller LLMs. So whereas a 7 billion parameter model was going to do something, is going to be great at something like code completion, it's going to be very bad at reasoning. And so you want to be able to use the best LLMs out there. And unfortunately, right now, the best LLMs out there are proprietary. They're not open source. That being said, if you use like DeepSeek, the reasoning model from DeepSeek, Llama 4 is also going to be coming out. Llama is also going to be coming out with a reasoning model. They are good enough to do this. So it is possible right now to set up an agentic system using open source LLMs. But really, if you want the best performance, unfortunately, this is one of those things that if you use a stronger base LLM, you are going to get better performance. And right now, that means going to an API. All right, so we had a couple of hands. Yeah.
Thank you so much for the talk. The tool that you're mentioning here is essentially function calling.
So that's exactly it. So depending on the provider, it has different names, but essentially function calling in the OpenAI terminology. Yeah.
So you said that cannot run things in parallel. Won't that also be an implementation detail? The second one.
Yeah, absolutely. Yeah. It absolutely is an implementation detail. There are some architectures for building agents right now where you do things in parallel, or you do things paying attention to the axis of time. So it's trying to accomplish a task within a set amount of time as well. But unfortunately, like most of the agents that are out there right now are very serial in nature. Did we have? Yeah. Sorry, I didn't hear that. Okay, so the question is, what are some useful techniques for reducing hallucinations? So relying on factual data or real-time data is the most powerful thing I would say. If you leverage the LLM's weights for knowledge retrieval, you're gonna be very prone to hallucinations. So and the reason for this, you have to view LLMs as kind of a condenser or a compressor of information. So for example, let's say in the training data, there's all the Harry Potter books. It's not gonna like store the Harry Potter books in its weights. It's gonna learn something from it. And what it might learn is kind of the general storyline, the general plot, and you can ask it about the general plot. But if you asked it like, what is the fifth word on the second page, it's not gonna be able to do that perfect recall just because it saw it in its training data. And so what you really want to do, so that's we're talking about this case, right? It's not able to do that perfect recall. So what you really want to do is you want to combine, your prompts or the context for the task with the relevant piece of information. So if I wanted to ask it, what is the fifth word on the second page of the first Harry Potter book? The best way to reduce the hallucination is to actually give it the Harry Potter book. Now, the difference between agents and what I just described is in this case, I have to have the book available and I have to know to give it this book. But with an agentic approach, it can go maybe search for the book, or it can access a repository of books and basically be able to build its own context. But really, to kind of answer your question, to reduce hallucinations, You want to move away from using LLMs as knowledge bases and more towards using LLMs as a reasoning kernel, as the reasoning core of a system. And kind of the knowledge and information it's accessing from outside. Yeah. Okay, I'm just gonna take a couple more questions. We do have MCP to talk about. So, yeah, I see a couple of hands. We'll do you guys.
Hi. So, I've been in the ML space for a while, but the way you articulated the presentation before you was incredible.
Awesome.
For that. Here's one question. Maybe it's like a subset of this conversation today, or maybe it's not. So, let me know. You know how GPT-4 was really incredible compared to GPT-3?
Yeah.
And DeepSeek came in and then made it everything open source, gave the weights to people,
Yeah.
allowing them to create these things on their on their own side.
Sure.
I know there were some articles about how like if OpenAI went kind of like what's the right word to articulate it? They bent some lines in order to scrape, right? But DeepSeek bent more lines on OpenAI to do those things. Can you add some clarity into how the engineers at DeepSeek may have approached it by by going the gray area on OpenAI?
Yeah. Yeah. It's a deep question. So I think any LLM. Sure. Basically, the question is, can we talk a bit more about, and correct me if I'm wrong, but this is how I'm interpreting the question. Can we talk a bit more about the ethics of scraping and getting access to data and how that influences the performance of the LLM? Yeah.
But there was massive scraping done
Yeah.
by OpenAI.
Yeah.
It's another question if it's right or wrong.
Sure.
DeepSeek also did the same thing, but
Yeah.
they took shortcuts to OpenAI.
Oh, I see.
So that's
Yeah.
what I'm trying to understand. I'm not trying to
Yeah.
be the police world.
Sure. So did DeepSeek use OpenAI for training? Yeah. Well, I'm not sure. And as far as I know, it's an accusation. I don't know if it's been substantiated. But for a bit of context, there is a rumor that DeepSeek used outputs from GPT-4 in training their own model. It's possible. And one way, let's say they did it, the way they would have done it maybe is for the post-training part of things. So for like stuff like RLHF, where you're not training on text data, you're training on preference data, you're training on ranking data. So you have two answers, pick the better one, and you can somehow adjust the style or the tone of the model through this preference data. So this type of data is very hard to collect because you need hundreds or thousands of human annotators. And so what they might have done is maybe automate that process by using a really smart model like GPT-4 to do the ranking or to do the preference, and then use that data to do the RLHF loop for their model to kind of do that post-training and alignment and stuff like that. Yeah.
But one thing is, how in websites people do rate limits, right?
Yeah.
There has been an issue where OpenAI forgot to put guardrails on rate limits, and that's why DeepSeek was able to do that. And now if somebody else tries to pull a DeepSeek on OpenAI, they can't.
It's possible. Yeah, I mean, it's possible that OpenAI is more looking at this stuff more carefully because of these accusations. Maybe they're going to lock down very large scale access to the models. It's possible, yeah. But to kind of get to the core of your question, I do think that right now we are capable of training a DeepSeek level model without having to scrape OpenAI. I think there is enough data out there. I think there is enough computational resources out there to do this independently. And honestly, like data quantity isn't even the biggest limit anymore. We're hitting a point where data quantity doesn't matter that much anymore, where if you double the size of the data, you're not really going to get that much more performance out of the model. Data quality is a much bigger concern. Okay, last question. Although we could honestly, so I was going to talk about like MCP, model context protocol. Maybe we can like take more questions since everybody seems to be very interested in this section. We can kind of skim over this. So I'll do a couple more questions. All right, in the back there.
Really practical tips when it comes to bringing a new product to market. How should one do that?
Yeah. Yeah. So the question is, do I have any tips for bringing an agentic product to market into production? I think one of the biggest things when you come to production is going to be reliability. So it's really easy to build cool demos with agentic AI. It's really easy to build a very cool demo that works in a constrained environment, but fails miserably on the kind of the easiest edge case. And when you go to production and you start using it for real use cases, it's going to be all edge cases. And I think one of the things that gets missed a lot is reliability. And it's really important because reliability affects your users' trust. When you use a product and it's hallucinating or it's just kind of bugging out, you're not going to trust it anymore, and you're not going to use it anymore. So my biggest thing I would say when going to market after building a demo is to focus a lot on reliability. And how do you ensure that? How do you measure that? So a big part of this is going to be benchmarks. So you need to quantify the reliability of your system. You need to quantify the performance of your system. It's not enough to just use it kind of manually. It's not enough to just kind of do a demo and it kind of works. You need to kind of have a large scale quantifiable benchmark. And this is a very difficult thing. And so, yeah, I would say focus on reliability, focus on measurement of reliability and performance. Yeah. Yeah, sure. I mean, you can come up with a data set. I mean, it highly depends on the task, right? But you can come up with a data set of known prompt answer pairs. So let's say you're building so if you're building a calculator, let's say, it's really obvious. And you can generate these examples and you can also verify them. Let's say you're building something a bit more abstract. Let's say you're building like a travel advisor. You're building a system that can search the web and look at the map and recommend places to travel for people. And so how do you come up with like, known answer pairs? Like, I want to go to Paris, where should I go? And then, the Eiffel Tower is a reasonable answer, but the Louvre is also a reasonable answer. And it's really hard to verify that because also the output is going to be like a natural language and stuff. And so what you can do, a very common technique when you talk about benchmarking is using an LLM as an evaluator. And so when you have this data point in your benchmark set and you want to evaluate, did the model achieve the task correctly or not? Instead of writing a program or a bunch of conditions, you can actually use an LLM to make that evaluation. So that's a very common technique as well. Yeah, I hope that answers your question there. Okay.
Can you take that example a little bit further? Let's say I want to go to Paris.
Yeah.
And giving it 4 prompts, like even the top 5 destinations.
Yeah.
Check out when I'm in Paris. How would you task an LLM to qualify the answer?
Sure. So you can have a system prompt that's like, if it didn't follow the instructions, give it a 0. If it followed the instructions, but suggested not the right amount of things, give it a 1. You can kind of create a rubric in natural language, and then parse the outputs that way. Yeah.
the new agent which basically validates.
It doesn't even have to be an agent. It can be as simple as just an LM. And here you're not evaluating kind of necessarily, you know, did it output the best destination in Paris, but did it just do the task successfully? Did it output a destination in Paris or something like that? I think this is not a great example. I'll give you another example maybe. So let's say you're building a system to do code reviews. So let's say you have a company and engineers are putting up code reviews all the time, and you want to create a data set or create a system that can predict if a code change is going to cause a bug, right? So you can create a data set of all the previous code changes that ever caused a bug. And you can train a model on that to predict, okay, given a new code change, is it going to cause a bug? But let's say you wanted to fine tune a model on articulating why it's the bug. And so you go back and for all of those previous code changes that cause bugs, you want to generate or somehow get a summary of how it caused that bug. So now you have a data set of natural language reasoning to bug caused pairs. And you find a data source, like maybe your company has an internal tool where it tracks like urgent events. And you're like, hey, if I scrape the descriptions, I bet that will be a great reasoning for why this code change caused the bug. But then you learn that some engineers don't fill out the description, or they just paste a link in the description, or they paste weird stuff in there. If you were to come up with a bunch of hard-coded rules for figuring out is the description relevant to the bug or not, it's gonna be really hard because you have so many edge cases. You know, maybe it's a link, maybe it's text, but it's formatted weird or whatever. And so instead what you can do is use an LLM as an evaluator. So you have an LLM and be like, hey, I want to use this data source as the reasoning for why this code change caused the bug. So this is going to be my evaluation data set. And so this LLM can have the task of determining whether or not these things are just relevant at all in the first place. And if you wanted to do this at really big scale, really fast, you know, you can also just use embeddings. You can look at semantic similarity to some degree. It's a lot cheaper way to do it. But yeah, LLM as an evaluator, that's an example of where you can do it. Where writing the rules for doing that validation is really hard when you have to do it by hand. Yeah. Yeah. Okay, in the back there.
If you have to compare RLHF and HBOT, which one would you think had a bigger impact? Or the second one just shadow versus synergy?
Oh, absolutely RLHF. Yeah, like.
How relevant are they still in an agentic system?
Yeah, a great question. Great question. So the question is, you know, what's more important, chain of thought or RLHF, and are they still relevant? So RLHF is the huge breakthrough that makes LLMs usable, honestly. And actually, right now we're seeing a huge shift away from pre-training, so just next token prediction on a very huge corpus of text, towards post-training, RLHF alignment, this kind of fine-tuning. So RLHF was, you know, you take this base LLM, which is just completely unhinged, and you're able to give it a personality. You're able to give it, you're able to make it useful, essentially. And the way RLHF is related to agentic AI is you can take traces, or they're called sometimes trajectories. You can take previous chats or previous examples of an agent trying a task out. You can take that trace of it and feed that into an RLHF loop or other kind of RL techniques for post-training. Maybe not RLHF specifically. There's a bunch. There's like DCP and a bunch more. But basically what post-training allows you to do is train your LLM to be more like an agent. So let's say you know you're going to have a tool where your LLM can write and execute Python programs, and you want it to get better at writing and executing Python programs. You can have your agent use your tool. It's never seen this tool before in its training. and now you have generated a bunch of traces of this. Now you can take this data and using post-training techniques, feed it back into the model. And now the model that you're going to get out of that is going to be better at using that tool. And that's exactly what something like ChatGPT is doing. They're training on chats. So they're training on trajectories, like, in this chat, it wrote this kind of Python program and it actually ended up failing. When they do their next training run, it's probably going to be a bit less likely to do that. It's going to somehow learn from that interaction. It's going to somehow learn from that mistake that it did. So RLHF and just post-training in general, huge deal. And it's a big part of why this new generation of LLMs is so good at agentic stuff. Because they're being trained to be good at agentic stuff. Like, this is a big focus when we talk about foundational models. It's a big focus for the capabilities that we want to get out of them. Yeah. Okay. So we have an hour, Mark?
As much time as people want to spend.
Okay. Well, I mean, people don't seem super bored out of their mind yet. So maybe we'll do MCP in 5 minutes. Okay, but do we have any other kind of last minute questions? Okay, yeah.
Spoke about training models based on benchmarks. I'm not sure if you've seen the release of the new Llama model, and there was a bunch of programmers asking the model to program stuff that is pretty basic, like spin a object and balls can go through the lines, or how many R's are in the library.
Sure.
So they tested that
with
this new model and it failed miserably. So there was discussion that they used benchmarking, ranking to train.
That's a great question. So so the question is like, when they're training Llama, it seems to perform really good on benchmarks, but then when you ask it how many R's are in Strawberry, it fails miserably. So what's the deal with that? So I think, there's a lot of things happening there. So number one is, the whole like R in Strawberry thing, it has to do with the way LLMs view text. So they don't view text character by character, they use tokens. And so when you give them a word like Strawberry, they might see that as one token. So they're not actually able to kind of decompose it and break it down. Whereas if you combine Llama 4 with a tool where it can write and execute Python programs, I bet it can tell you the number of R's in Strawberry, right? So if you built an agentic system, it can absolutely do that. But the base LLM itself has severe limitations. And a big part of that limitation is just in the way it even perceives the text in the first place. So that's why it fails at something like how many R's are in Strawberry, because it's not even able to see the R's. It's just seeing Strawberry as a single token, a single symbol in its vocabulary, right? Now, but to kind of get to the gist of your question, when we talk about benchmarks, that's a huge deal. There's a lot of papers that are showing that a lot of benchmarks are poisoned, that a lot of LLMs have been trained on the benchmarks that they're getting evaluated on. And it's a really big concern. And it's kind of hard to fix because they're scraping the internet. And if your benchmark gets onto GitHub, then your model's going to see it. I'll tell you how something like OpenAI is dealing with this. So a very important benchmark at OpenAI is the loss on their internal code base, on the code base of ChatGPT itself, because they know it's not public. They know it's not in their training data. And so they evaluate their model on its own code base. And they say that that's a very strong indicator of its performance. So you have to find ways to get benchmarks that your model is never exposed to. You have to find ways to get. So you might create the benchmark after you train the LLM, right? So that there isn't even a chance. But also benchmarks can be very hard. So for example, you have something like SweBench. This was a benchmark where at the beginning of last year, I believe the best LLM had like 5% success rate, and now it's like 80 or 90. And SweBench, it's like it doesn't have an easy answer. And so even if you showed a model an example solution to a SweBench question, it might not be able to replicate it. And so, part of it is also just having harder and harder and harder benchmarks. Yeah, if you see a benchmark that's kind of plateauing in terms of performance, or it's kind of like 80-90% successful, it's saturated, it's not very useful. And if it's like the difference between 92 and 89 is not very useful. So whenever a new model is released and it's like we're 2% better, it's not very meaningful, right? And so you want to keep looking towards these harder benchmarks. You want to keep looking towards these newer benchmarks that they couldn't have possibly seen yet. Yeah, for sure.
How's everyone doing? You want to stick in for a half hour? Do some MCP?
Okay.
What do you think? Good?
Yeah, let's do it. MCP in 5 minutes, everybody. Okay, so when we did our history, we said, okay, LLMs, we can build agents by combining them with memory, by combining them with some sort of planning mechanism, and by combining them with tools. And tools are a very generic concept. It can be an API, it can be a database, it can be the file system on your computer that you wanted to be able to read and manipulate things on your computer. There's all kinds of tools out there, and there's all kinds of models out there. How do we, and everybody's building their own implementation between these things. How do we standardize this? And that's kind of where MCP, or the Model Context Protocol, comes in. So MCP is a protocol, so it's an open standard that aims to simplify or standardize the way we connect LLMs to data sources and tools. And it's inspired by LSP, or the Language Server Protocol. So I don't know if you guys remember, before LSP, you have your IDEs, VS Code, Atom, Vim, and you have your languages. And if you want to use that language in that IDE, somebody had to build that integration. Like JetBrains had to build support for JavaScript. VS Code had to build support for Python for you to be able to use Python and VS Code and get autocomplete or whatever. But with LSP, they created this standard way where you build a language server. So you just have to create a LSP compliant server for JavaScript. The IDE implements support for LSP, and then you can just use anything that has an LSP server in that IDE. So instead of having M times N connections, we have M plus N connections. And so that was a really important thing for LSP. MCP is basically the same idea for language models and data sources. Instead of building a connection between every single AI application and every single data source from hand every single time, we can just build an MCP server around that data source and integrate it into our IDE. This is going to make sense a bit more. But basically, the motivation is we want to solve this M times N implementation problem. You're going to have pre-built integrations that you can use. So you don't have to go figure out how to incorporate JavaScript into your IDE, or in LLM terms, you don't have to go figure out how to incorporate Google Drive into your agentic system. You can use a pre-built server around Google Drive, and all your application has to do is just support MCP, and you can plug in all of these things. It's kind of like plugins, but in a standard way. And just kind of a use case. Let's say you want to build, like a customer support chatbot. The way you would do it without MCP is you have to go and integrate a bunch of different APIs. You have to go glue a bunch of different APIs together. You're going to need a API for your CRMs. You're going to have to go figure out how to do auth with Salesforce. You're going to have to go figure out input-output serialization for the Salesforce APIs. You're going to have to do that probably 10 times for 10 different APIs. With MCP, Salesforce itself, or the community, is going to have an MCP server already available. And so all you have to do is make your application support MCP, and you can plug and play these different servers. I was going to kind of go into the architecture of MCP. Maybe we'll skip over this, but basically MCP, it's client-server architecture. You have your host, which is kind of your application. It has a bunch of clients that create connections with MCP servers. Yeah, we're going to skip all over that. Servers expose tools to clients. So a server is going to have a list of tools or capabilities or functions like function calls as before. And it's also going to have a list of resources. And your host or your client can list all of the resources and tools available to it across all of its servers and be able to use them in an agentic way. And so this is kind of like what the simplest MCP server looks like. This is using something called fast MCP in Python. You define your function, and this is going to get exposed to whatever model plugs this MCP server in, and is going to be able to, for example, add two numbers together. There's a huge amount of growing. There's a big ecosystem of MCP servers that's continuing to grow. So, for example, there's a Google Calendar MCP server. There's a GitHub MCP server, and you can just plug and play these things. Yeah, I'm just kind of going through this very fast. I'll give a live demo at the end, just to kind of give you an idea, make it make a bit more sense since we're going through it so fast. But things to note with MCP, it's a very thin protocol. There's a lot of hype around it right now, but really it's quite a simple thing. Things to note, the S in MCP stands for security, and you'll notice there's no S in MCP. So a big, you know, a big deficiency right now is that the protocol itself is not necessarily secure. A lot of the security is left up to the discretion of the users, and there's a lot of kind of vulnerabilities as a result. So you're opening up to like prompt injections, data leakage, tools kind of doing the switcheroo on you. It's a huge security surface area. There's not a huge amount of adoption yet. There is some adoption, but there isn't a huge amount. For example, ChatGPT doesn't support MCP yet. You can't just plug and play MCP servers into ChatGPT. And yeah, okay. So I'll do a very quick live demo of MCP. I'll do a very, very quick live demo of MCP. I don't know if any of that made sense at the speed that we just did it, but I'll give you guys an example.
It's like APIs for LLMs.
Kind of.
I have a question.
Yeah.
So I've tried using a few MCPs.
Yeah.
And I use like the client plugin. And I found that a lot of servers, like, they're distributed in a whole bunch of different ways.
Yeah.
Solve like protocol N by M, but now like some are trying to install through NPM, Python, Docker.
Yeah.
Do you have any comments on that? Like,
Well,
yeah,
I think what's going to happen is, yeah, they're distributed in a bunch of different ways. I think what's going to happen is we're going to move towards hosted MCP servers, where the service provider is going to also host the MCP server. So when you want to use a Google Calendar server, instead of having to install something on your computer that can talk to Google Calendar, you're just going to your host is just going to remotely connect to Google's hosted MCP server for Google Calendar. It's basically like just making applications, AI friendly or whatever.
Basically an LLM interface.
Yeah. Yeah, and I'll give you a very simple example here. I'm in my IDE, this is VS Code. I'm coding away, and I'm like, okay, I want to create, I don't know, I want to create a repo on GitHub, okay? I want to create a repo on GitHub. So, hey, can you, oh God, I'm writing all caps, a repo on GitHub. And, it's not going to know how to do that, right? It's like, hey, if you want to create a repo on GitHub, do all this. And I'm thinking, man, this thing's supposed to be an agent. This is kind of stupid, right? And so, okay, before MCP, the way you might solve this is you would wait for VS Code to create a GitHub integration, right? So now, VS Code is going to go do the integration with GitHub, and now finally I can use it here. But VS Code recently introduced MCP support. So what does that mean? So that means I can now go and install an MCP server for GitHub. So I just Google MCP server GitHub. So these fine gentlemen and ladies have built a bunch of MCP servers, and one of them is GitHub. And so this allows an LLM to interact with GitHub. And this server might be hosted remotely. In this case, you install it locally. So I'm going to click this button. Okay, so installing MCP server. I'm going to maybe configure it. I'll give it my GitHub personal access token. which I've written down somewhere. Kind of hard to see. Oh gosh. Hang on, I'm gonna turn off mirroring. I think I've muted myself. Please don't have guys. Remind me to delete this token. Okay, there we go. Okay, so I'm installing this MCP server. I'm gonna paste this token here. Yeah. Okay.
It's not easy enough to steal yet.
Okay, install server. Okay, so now I have this MCP server installed, okay? And I'm gonna start a new chat. And I'm gonna go into agent mode. Put on my glasses. And you can see, look, it has a bunch of tools now. Get issue comments, create repository, create pull request. And now I can say, hey, create me a GitHub repo called foobar-baz. And look at that. It's like, hey, it's telling me I want to run create repository. And so I'll tell, okay, go ahead. And so now this LLM is taking an action. It's reaching out to the environment and taking an action. And this is the beauty with agents. They can do stuff. And okay, I've created the repository. You can access it at blank, blank, blank. And there you go. It created a GitHub repo. Now, I want to highlight something. So you're probably thinking like, okay, what's so special about this? Like, it just called some APIs, right? The key thing to note about MCP is this M times N integration problem. VS Code did not create integration for GitHub. GitHub did not create any kind of special support for VS Code. They both just implemented the MCP protocol, and now I can just plug and play this MCP server. And so let's say you're at work, you want to give this agent access to a database. You want it to be able to run, write and read queries. You can create an MCP server, hook it up here. But let's say your coworker uses Vim, or your coworker is using Claude desktop chat client. They'll be able to get kind of the same capabilities in their client or in their application without any additional integration work. So that's kind of the example there for MCP. We're able to add capabilities to agents without facing this M times N implementation problem. Yeah, that's pretty much it. So any questions about MCP? Okay. So the question is, if I understand correctly, what's the difference between creating your own tools for your agent? Okay, so let's say you wanted to build an agent that can talk to GitHub. Let's say you're building a chat app. You wanted to be able to talk to GitHub. Is your question, why don't I just integrate with the GitHub API directly? Why should I use the MCP server for GitHub? Right. So let's say you want to support GitHub. Somebody has built an MCP server for GitHub. Let's say you want to use GitHub and Google Maps, right? And they both have MCP servers. If without MCP, you would have to build an integration for GitHub and then build an integration for Google Maps. You'd have to kind of build some adapter code between your application and their API. Instead, all you have to do in your application is support MCP. Once, support MCP. And then you can plug and play these MCP servers. So you don't have to build, if you have N things you need to support, you don't have to build N different adapters for their APIs. You just have to implement MCP and plug and play the already existing adapters. Yeah, very, very convenient to use. But it also has other advantages. So this is kind of on the application side, on the client side. But you can also think on the server side, it's very useful, right? So let's say you have an API or you have a service that you provide. You can imagine that you want to standardize the way people talk to your service. You want to standardize the way, not people, sorry, AI interacts with your service. So maybe there's certain access patterns that are more efficient, or maybe there's certain APIs that you want to prefer. So if you create your own MCP server and you release that, then you're basically standardizing the way AI talks to your system. So also for the server developers, it's also a very useful thing because you're kind of condensing all of the different ways to interact with your service. There's also another thing this unlocks. So MCP servers don't have to be remote. They don't have to be APIs. So for example, an MCP server can be local, and you talk to it through standard input, standard output. And so you can have a file server MCP. You can expose agents to the file system on the computer. Or for example, you can imagine desktop applications shipping with an MCP server embedded. So Outlook, for example, is going to start shipping with an MCP server. And now if you have some AI system running locally, it'll be able to interact with the Outlook application running on your computer if it supports MCP, right? And you don't have to build those integrations from scratch every single time. Yeah.
So in other words, MCP is a protocol that all applications, they agree to talk in the same language. So simply put.
Yes.
So in terms of how to pick one individual, but for every individual application, it's still up to the individual application vendor, the company to make their application compatible with the MCP protocol.
Yeah, exactly.
MCP protocol is just a common language.
Yeah, it's just an open standard. It's a specification, and yeah, it's up to the vendors, and yeah. So there's a lot of vendors that have onboarded, and there's a lot that haven't. So a big one is ChatGPT. So the thing I just did, where I just installed this GitHub server, and now boom, the chat in my VS Code is able to create issues and repos on GitHub. You can't do that on ChatGPT because they have their own like plugin framework, their own kind of proprietary thing. So time will tell where adoption takes us with MCP. But there is a lot of positive momentum right now, and it seems like this is going to be the protocol for linking LLMs to data sources and tools moving forward. Yep. Mm-hmm.
And we seem to be that MCP are a good place for just general businesses to offer services to these agents.
Yeah.
So they need to be a consistent approach to say, hey, I can enable you to open to me right up straight
Yeah.
to the site. I'm giving you a that's something you see or.
Yeah, absolutely. I mean, I think that this year and next year is going to be the explosion of exactly what you just described because of what MCP is going to enable. So before you had to depend on the whatever platform you're using to support the thing that you want to use. Now users have a lot of control. You choose which servers you want to install or not. You can build your own applications or choose what application you want to use. And I think the fact that it's an open standard as well, there's going to be a lot of community servers. So let's say you have a company that doesn't care about MCP, or you have a company that has an online store, but they're not very like tech savvy, so they don't really have like good APIs or whatever. You can have a community server, community maintained server for that service. And so, yeah, I think we're going to see a very large proliferation. We're already seeing it of MCP servers, and it's going to enable, really cool assistant workflows. Does that kind of answer your question? Yeah. Okay, in the back there. Yeah. Yeah. This is a really important question. So, okay, I have my LLM. I've plugged in a bunch of MCP servers. The MCP servers expose 20, 30 different tools. But when I ask my LLM a question or I give it a task, sometimes it's not calling the tools. Sometimes it's not calling the right tools. And how do we get around that? So this is a very important question. And there's kind of two groups of thought here. One is, let's have the simplest, smallest number of tools possible, but they're very powerful tools. And this is kind of this is what ChatGPT does. It doesn't have very many tools, but it has the ones it does have are very powerful. Web search, Python code execution, right? So it has a few simple tools, but it can do a lot with those things. And it's very unambiguous, like which tool it should choose for which task. And it's also very easy to train because they can take these trajectories, these traces of previous tool usage, conversation history, and use it to train new models. The other camp, which is kind of what MCP is promoting in a way, is let's give it 100 tools, let's give it 1,000 tools. And when you get to that point, what happens is LLMs start to get confused. So let's say you have two tools from two different MCP servers that look like they do the same thing. It might not know which one to choose, right? Or it might choose one, or it might not choose a tool at all. It might just rely on its weights. And so a big part of that, so to get around kind of this problem when you have many available tools, number one is you want to use the smartest model available. Smarter base models do better in an agentic setting. And so if you're using GPT 3.5 versus 4.0, you're going to notice a big difference. 4.0 is going to know better to call these tools. That's number one. Number two is the next generation of foundational LLMs are being trained for tool usage. Tool usage is one of the biggest topics in LLM research right now. So in the very near future, we're going to have a generation of LLMs that are way better at this stuff. That's number two. Number three, the way you define your tools is very important. And so, for example, here this tool in FastMCP, it's an add function or whatever. What the LLM is going to see, so LLMs at the end of the day are text in, text out, right? So what the LLM is going to see is going to get a prompt. So the application that's hosting the LLM is going to give it a prompt. It's like, hey, you have these tools available to you. One is called add. It takes two numbers. It has this description, right? And so the way you define your tools is really important. So you want to make sure your tools have good semantic names, have good descriptions, have good natural language descriptions for the LLM to understand when and how to use that tool. You can go back to when we were talking about few-shot prompting, give it examples of inputs and outputs to that tool. That helps a lot, right? Because they can do that in context learning like we showed. Another thing is, so MCP has something called roots, client roots. And this is something where you basically limit the capabilities of your servers. And so let's say, let's say we're in VS Code and I'm in a big repo and I've got 1,000 files. So the MCP server for the file system has thousands of resources available to my client. And when we get into an agentic setting, it's not going to know which file is relevant, right? But you can imagine, by using client roots, you can actually define boundaries. So you can say, okay, do this task, but only use the open files, or only use the files active in the workspace. So that's one example. Or in the case of tools, you can say, only consider the read-only tools. So I want to so I know that I want to fetch something from GitHub. I don't care about create repo, create issue, whatever. So if you limit the number of available tools, you're much likely to get success from choosing one of those tools. And so client roots is the way that a host or an application can help out in that sense. Yeah. And finally, it has a lot to do with your reasoning loop and your system prompt. So when you have something like the chat in VS Code or something like ChatGPT, what they really want to do is have a 2, 3, max 4 turn conversation with you. And so so they're trained, they're prompted, they're very heavily encouraged, and sometimes they're cut off to have a very short conversation. And to give you a prompt response, a timely response, right? And so they might not try a tool if it fails. They might not try it again very many times. They might not explore, let's say, very much. But I would encourage you to write your own LLM loop and say, hey, don't give up. Keep trying all the tools available to you. Make sure you use these tools. And so kind of creating your own loop. You might find that it'll take 5 minutes to complete the task, but then it might be a bit more exploratory. It might kind of be more likely to make use of those tools. So yeah, that's kind of a long answer, but those are some of the ways you can get around that. Yeah.
Two small questions. I guess first one is there a way to know which ones are vetted? Like you should, I guess, be cautious of whichever MCPs that you do hook into because you don't.
Yeah.
You don't necessarily know what's on the other side of those tool calls.
Yes, absolutely.
If it's an unvetted provider.
Yes, yes. And like I said, the S in MCP stands for security. So your client might be sending data to these servers, and who knows what these servers are doing with them, right? So ideally, maybe use an open source MCP server. They're much less likely to be malicious, right? Because they're going to be community maintained or something like that. And I think that, you know, exactly because of this risk, basically all MCP servers are going to be open source. So even when Google creates an MCP server, like a first party kind of MCP server for Google Calendar, for example, my very strong suspicion is that such things are going to be open source because of that trust factor. Yeah.
And then the other one is, do you also encounter context window lengths if you have like too many MCP servers and subsequent tools for each of those servers?
So you plug in 100 MCP servers, each one has 100 tools, and now when you go to prompt your LLM and your application is like, okay, you have these 10,000 tools available to you, and each tool is going to have a description and a name and whatever. Yeah, absolutely. You're going to run into context window problems. Yeah. And I mean, thousands of tools, it's not even, I mean, don't even think about it. So, because one thing you gotta note about context windows is they're kind of a lie. So, you know, you have models claiming millions of tokens of context window, but the reality is they don't pay attention to the entire context window equally. So they might pay attention to the first 128,000 and the last 128,000 a lot more. And so really, when we talk about full attention, beyond 128,000, you're gonna get a lot of lossy stuff. So yeah, you wanna.
I didn't think about this, and this is maybe a bit deeper on like the transformer architecture side, but because of like the attention mechanisms, does it actually work like, you know, human brains too? Like, you know, you always give weight to like the first thing and last thing that you encounter in any interaction?
Well, that highly depends on the implementation of self-attention. Yeah, but some of them work like that. And okay, so just to go a bit deeper here, so attention is quadratic in nature. And the way transformers work in the base architecture, the original architecture, is that the longer the context window is, you're going to require quadratically more memory to pay attention to everything. But in this architecture, it's full attention. So every single token is looked at, is considered, and all of that, right? So if you have a number hidden somewhere in the context window, or you have a very tiny detail somewhere in the context window, it will be able to pay full attention and fully recall that number in, right? But it's quadratic. And so beyond thousands of tokens, you're going to run into huge problems. So all current LLMs that use transformers, they're going to use smarter ways of implementing attention. So for example, one is called grouped query attention. And this just approximates attention. And so it's a bit weaker attention, but it might be linear in nature. So now you can scale up to 1 million tokens, but you can't pay as exact attention or as perfect recall to anything in the prompt. To get around that, what they'll do is the first 10,000 tokens, they'll say, okay, pay perfect attention to these. And then they'll encourage you to put your system prompt in the beginning of your query, or your instructions at the beginning of your query, or something like that. Yeah. So it's a bit of a hybrid model. But yeah, so yeah, the context window, when something has millions of tokens of context window, it's not perfect. There is going to be some loss there. Like this is very lossy. Yeah. Yeah. Any more questions in the back? Sure.
As of mentioned, every model is
Yeah.
so maybe the reason the representation, right? So more or less, right? They might use like related. They don't really like. They put in the output with the same.
Okay, so there's some nuance there. So when we talk about reasoning, so there's when you, it's gonna go all the way back here. So when you talk about reasoning, there's a lot of different models of reasoning. So when you give an input to an LLM and it gives you an output directly, you can say it's doing reasoning internally. It's doing its reasoning in some latent space between its layers, like that. When we talk about something like chain of thought, it's outputting tokens and it's doing its reasoning in token space, let's say, where because it's writing out some chain of thought in text, because it's outputting these tokens, because you're doing multiple passes over it, somehow that's going to lead to a better result. And you can call that reasoning as well. Kind of, yeah. Yeah, but there's a third type of reasoning, and this is called latent space reasoning. And this is like super hot off the press right now. And there's some rumors this is how O3 works. And with latent space reasoning, instead of outputting your thought process in tokens, you kind of just chop it off right before you output it to tokens and feed it back in. And so it's doing its reasoning in latent space, in the hidden space. And then after doing a bunch of these loops, it outputs some tokens. And so it's yeah, and yeah, this is like a really hot topic right now, and probably the next generation of reasoning models is going to be trained using latent space reasoning. Yeah. So but the risk of that, the problem with that is we will lose the ability to figure out what it's thinking about. Because right now when it outputs its chain of thought, it's like, the user wants this, I should consider this tool. Okay, I'm calling this. We can literally read that. But when we do latent space reasoning, it's just going to output the result or the action. We're gonna and we're gonna have no visibility into its thought process. Yeah. 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 Sure. Yeah. Yeah. Right. Yeah. So yeah. Well, okay. So here's the thing. So, I mean, up to this point, we're talking about language agents, right? LM language-based agents. But there's a whole new set of architectures now that are multimodal, and so they can take inputs in visual space, in audio, and text. They can do this latent space reasoning, and maybe even output any of these modalities as well. Yeah. Yeah. Right. Yeah. Yeah, well, yeah, maybe it's a problem if the goal is to replicate humans, but maybe you don't have to replicate humans to be useful. And so if you view it that way, that's not a problem. It's like, it's okay, they can reason like that. But when you talk about this latent space reasoning, I mean, you look at the mountain, you're gonna have some internal representation in your head of the mountain that's very abstract and very separate from the actual concept or the actual object, right? When we talk about this latent space reasoning that I was saying, you have these multimodal inputs, images, text, audio, whatever, but they're all going to be reasoned about in the same space. And so it's going to get multi-sensor input and is going to map it into the same latent space. And in a way, that's kind of what brains do. if you squint really hard, really, really hard. Yeah. But yeah, no, I mean it's an interesting question. It's really good to consider, like, how does this relate to the human brain or something like that? Yeah. Yeah.
I feel like this is like MCPs, like the language model does the reasoning before they have any knowledge of functions. So there is that disconnect between
Yeah.
the reasoning and the actual.
Yeah.
Maybe there is like market sort of where they can
Yeah.
actually use their mistake, they get a feedback.
Yeah.
Next time when they reason,
Yeah.
found it.
Yeah. And right now that's all happening in the token space. Like yeah. But I see what you mean. Yeah. There's also kind of one big difference is also with MCP and kind of LLM agents is it's discrete. It's taking actions in lockstep. Whereas when you consider something like the human brain, it's kind of a real-time continuous thing where there's constant input, constant outputs. Yeah, anyway. Maybe that's a good philosophical point to end our discussion here. Yeah, that's pretty much it, everybody. Agents and MCP, and yeah, I hope you enjoyed the talk.